So it turns out that our cunning Anzatz technique that we used to solve the problem in the previous video is actually applicable anytime that you want to solve a second order linear differential equation of the sort that we've been dealing with so far. So we're going to explore that in some more detail. It turns out that we can actually get quite a lot of interesting physical intuition by really looking quite deeply at the kinds of answers that we get when we use that technique. But first we need to formalize a couple of definitions. So the first thing we're going to do is define what's called a general solution to our second order linear differential equation, which, don't forget, is homogeneous and has constant coefficients. So a general solution is formed by taking two specific solutions which both satisfy the differential equation and then forming a linear combination of them. So our general solution means you take two specific solutions and then you combine them with some factor. But it's not quite the whole story. There is a condition that needs to be filled in order for this to be a general solution. And that condition is that for any choice of t0, u0, and v0, so for any initial conditions, the constants c1 and c2 in our general solution can be adjusted so that our general solution satisfies the initial conditions u of t0 equals u0 and the velocity, so u dashed of t0 equals v0. So this property is quite important. We're going to see in a little bit what happens if you don't, if your u1 and your u2 don't match that criterion. A bit more terminology. The specific solutions that we use in linear combination to find our general solution are called basis functions, and together they form a basis set for the set of solutions to our ODE, and sometimes you'll hear them called the fundamental set of solutions. This should sound vaguely familiar if you've done any linear algebra, where you have a set of basis vectors and then you take linear combinations of those and those give you your whole vector space. And in fact, functions in this way kind of form a vector space of their own. So the terminology is kind of, it makes sense. Okay, there are two important things that we need to think about before we can dive into kind of practical applications. So the first thing to do is just kind of a generalization of the specific case we showed before, which was, so for our specific example up here, we showed, so we found two solutions, and then we vaguely kind of showed over here that any linear combination was also a solution. So we did this for our specific problem, but something you should do for yourself is basically just show that if you have two specific solutions satisfying a general linear second order linear equation of this form, then the linear combination of them is also a solution. And you should do that for homework. You can basically follow the computation that we did in the specific case. So that's one thing that it's important to understand, is that two specific solutions in linear combination give us a general solution. But this exercise is also important because this shows us that you can't just take any two specific solutions. In particular, if you take two specific solutions that are multiples of each other, so for example u1 is alpha times u2, it's going to turn out that you can't actually get any general solution. So remember, our definition says that you're a general solution if you're a linear combination of two specific solutions, and for any choice of t0, u0, and v0, we can find c1 and c2 so that these initial conditions are met. But what you should do for homework is check that if you pick a u1 that is a multiple of u2, then there are going to be some initial values u0 and v0 which you can't get a c1 and c2 for. So this is also important. And if you're starting to think that this sounds a lot like vectors, you're absolutely right. Essentially what we're saying with this property over here is that u1 and u2 must be linearly independent. So you can actually bring all your intuition from linear algebra in here if you've done any linear algebra. If you haven't done linear algebra, that's fine. What you're going to learn here is that we say that our u1 and our u2 have to be linearly independent. They can't be multiples of each other. If they're linearly independent, then we can put them together in linear combination to give us our general solution. If they're not linearly independent, then they're linearly dependent. So linearly dependent means one is a multiple of the other, and if you use them together, they don't give you a general solution. Okay, so that's a little bit of homework. These are not tricky, but that's just to give you practice thinking through these things. Okay, so as I said, we can use the Anzatz technique that we did for the specific case earlier in the general case. So remember what we said was our ansatz was that we're going to suppose that u equal to e to the rt is a solution. And then if you think about what we did, we plugged that back in, because in order to be a solution, it has to satisfy the differential equation. So we found the first derivative, which was e to the rt, then we found the second derivative, which was r squared e to the rt, and then we plugged it into the differential equation, and what we found was that we would have to have m r squared e to the rt, so that's this term over here, plus cr e to the rt, that's that term, plus k e to the rt must be equal to 0. And then we pulled out our e to the rt, so we'd have mr squared plus cr plus k e to the rt is equal to 0. And then we said, well, this e to the rt is never 0. So in order for our ansatz function, our u, to be a solution, it must be that this factor must be equal to 0. And that leads us to the first part in our procedure, which is saying, well, in order to make that 0, we need to find the roots. So this equation over here is called the characteristic equation, and you find the roots. And you can use good old quadratic formula that you've been using for years. So plugging in, you probably learned it as minus b plus or minus, what's it, minus a, you remember it, root b squared, whatever. But in terms of our m, our c, and our k, here are the roots of our characteristic equation. Now the important thing here is in step 2, we're assuming that our roots are not equal. So a little note here is this technique doesn't work if r1 equals r2, so if we have equal roots. So we need to deal with r1 equal to r2. Okay, so if they're not equal, then we just go straight ahead and we can form our general solution, which is c1 times e to the first root t plus c2 e to the second root t. And that's great. And then by what we said earlier, if it's a solution for any choice of c1 and c2, which is delightful. And if we have any initial conditions that get given, we can plug those in, and you could work all those out. And finally, although no one would ever do this in their right mind, based on initial conditions u of naught equals u naught and u prime of naught equals v naught, you could write down the specific solution. Okay, so here's our general solution, and then you've got our specific solution. Please don't learn these formulae. you don't need to. This is just showing the general solution over here. But just to reiterate over here, if R1 is equal to R2, then this thing over here is not a general solution. So that is a case that we will come back to once we've looked at these things a little bit more. Okay, so that's the general idea. I recommend reading through it, but really, in terms of what you need to know, is you find the roots to the characteristic equation, and then you go from there by following the algebra. You don't plug into these crazy equations over here. So this is a general formula, and it will always work, and you can always just find the solution, but it actually makes a lot of sense to think about the different cases that we have and what they mean physically. So what do I mean? Well, you'll notice that we have in our roots, we have c squared minus 4mk in both of our roots. And that probably is immediately, hopefully, flashing some warning lights, in that what we get out of that root is going to depend on whether c squared is bigger or smaller than 4mk. So if c squared is bigger than 4mk, then what we have inside the root is real, so we can take the root and get a real root. But if c squared is less than 4mk, then we're going to get imaginary roots. And it turns out that we get quite different physical modeling properties depending on whether c squared is bigger or smaller than 4mk. So we're going to spend some time looking at these different cases. So the first thing that we're going to do is think about possible values of m and k and c. Now, the discussion up to now has been completely general, and you could take any real values for m and c and k. So remember that m is our mass, and c we're thinking of as our damping constant, and k we're thinking of as our spring constant. But because more often than not we're trying to model physical systems, it makes sense to think about mostly situations in which our mass is bigger than 0, our spring constant is bigger than 0, and also our damping constant. So we're thinking specifically around physical systems here. And this also helps us break down the solution that we're interested in, because remember we're looking at finding the roots of the characteristic equation, which was mr squared plus cr plus k is equal to 0. So that's our characteristic equation, which we saw back up here, and we're finding those roots. And once we've put some kind of constraints on our m and our c and our k, we can really talk about the different cases for finding these roots in a lot of detail. So the first one that we're going to have a look at is the overdamped case, which in fact we've already seen. So this is where our c squared minus 4mk is bigger than 0. So just reminding you where the c squared minus 4mk came. This is when we want to find our roots. Here are the two possible roots of this equation, which we use just using the quadratic formula. And as we said, the thing that we particularly care about is what is going on under that square root, because that's going to determine whether we have real roots, imaginary roots, or a combination of the two. So let's look at the simple case first, where what's under the root is real, is positive, in which case when we take the root we get real numbers. So we're looking at when c squared minus 4mk is bigger than 0. Why do we call this the overdamped case? Well, you'll see physically in a moment, but here we're thinking about the fact that if we reorganize this inequality a little bit, we find that c is bigger than 2 root mk. So we're really saying that the damping coefficient, our c, is bigger than some factor of our mass and our spring constant. Okay, so this means we're taking the square root of something positive, so that means that we must have positive real numbers for our roots r1 and r2, and they're going to be distinct. And you can check that if you go back and have a look at this equation here, which gives us our r1 and r2. But we can actually go a little bit further than that. If you look at the formulae we had for R1 and R2, you can see straight off that R2 has to be negative because, well, let's actually do that. So we can see straight away that our R2 has to be negative because this term itself is positive, so the minus sign makes it negative. And again, and this bit over here is positive with a minus sign there. So our R2 is definitely negative. And we can also do a little bit of work, and you're welcome to talk through this by yourself, but you can find that R1 is also negative. So the upshot of both of these is that in the overdamped case, our R1 and our R2 are both less than 0. So when we plug those into our general equation, as we did over here in our specific solution here, you'll see that our solution in the overdamped case is going to be a sum of two decaying exponentials, because you will get an e to the minus something plus constant e to the minus something. So we can see from this, we know that in the overdamped case, no matter where we start, we're going to have a decaying exponential that heads towards 0. We can actually see a little bit more clearly the different kinds of solutions that we can get if we plot for some different values of the constants. So, for example, the first plot that I made here, this blue one, which is this line over here. So here I just took the U1 and the U2 that we found over here, and I let my constants equal 1, and plotted that, and we get the blue line over there. So you can see that it starts, our system starts at some point, and then it just decays towards 0. If you add in some non-zero constant, not some non-unity constants, so here I just took 2 times the first solution plus 3 times the second, and you can use that to adjust where you start, so we would have a higher intercept there. But that's not the only kind of system that we could model. We could also model, for example, a system, so over here, my first coefficient is negative, so I had minus U1 plus U2, and you'll notice that what happens is, in this case, I model starting at 0, ramping up, and then decaying back down. And you can imagine if you took different combinations, for example, minus U1 plus 2 U2, you might start slightly higher up if you're thinking about starting at time t0, up and then go down, or you could start negative. So you can get an increase but then a decrease and trending towards 0. You might also want to model something that starts at a negative value. For example, here I got 2 negative coefficients, and then I just gradually increase up towards 0. So depending on the coefficients that you pick for your specific system, you can model quite a diverse set of phenomena. But the one thing that you'll notice is that we don't have any oscillation, and if you look, the only case that we have here which crosses the x-axis crosses it exactly once. And you can in fact go a little further, and I suggest that you do for this exercise here, which shows that if you have an overdamped case, so this is a case where your two roots are both negative, and you're trying to model something which is really being damped down to no movement, then at most your system can cross the equilibrium position at most once. So you can cross the x-axis at most once. So I would work through this and prove that for yourself. So we kind of saw it in the diagrams, now do it theoretically. Okay, so that was the overdamped case. So this, for example, if you're thinking about it in terms of our building that was shaking, would be a situation where the strength of the building is such that the building tries to shake and it might get one wiggle and then it's immediately stabilized by the frictional forces. The next case that we need to have a look at, we're actually going to combine two cases together, is the underdamped case and also the undamped case, because they have a lot of similarities. But take a moment to just get comfortable with working with the overdamped case, and then when you're ready, come back and we will talk about the underdamped case and the undamped case. So let's start off by having a look at an undamped example. So this is a situation where we don't have any damping, so our C is equal to 0. And that's going to be slightly easier, and then we're going to come back to the underdamped case in a moment. And let's just look at a specific example. So we're going to take C is equal to 0 and just be super simple and let our mass and our spring constant be equal to 1. And then we get this equation over here, which is called the undamped harmonic oscillator equation. And we'll see exactly why it's called undamped in a moment. Apart from the fact that it has no damping constant, you'll see what the solution looks like and understand why it's undamped. So let's find the specific solution when our initial displacement is 1 at time equals 0 and our initial velocity is 0. So this should actually look very familiar from intro to physics. This is the first sort of simple harmonic motion equation that you will ever have seen. Just maybe go back and have a look at your notes if you want to remind yourself. But let's solve this anyway. Okay, so we know if this is the equation that we're trying to solve, then the characteristic equation that we use to solve this is going to be r squared plus 1 is equal to 0. And so we just go straight ahead and find the roots, and you have a look at this and go, it has no real roots. In fact, it just has imaginary roots. So it has the roots r1 is equal to I, and r2 is equal to minus I. If you're feeling a little hazy about complex numbers, please go and do a little bit of revision. We're not going to do a lot with complex numbers, but you will need to use them. So go and revise if you need to. Okay, so we've got our complex roots over here, so we can just go straight ahead and put this into our general solution. So our general solution is going to be u of t, which is equal to some constant times e to the it, so that's with our root 1, plus some other constant c2, e to the minus it. So one of the things that you will notice about our roots here is that they are conjugate of each other, and that's always going to be the case. When we have imaginary solutions, you'll have two roots and they will be complex conjugates of one another. Okay, so we've got our general solution. Now we want to find our specific solution, so we need to put in our initial conditions. So to do that, so we want our specific. Well, u0, so u at time t equals 0 equal to 1. If we plug that in, that tells us we need to have that 1 is equal to c1 plus c2. And if we plug in that the first derivative at time t equals 0 is equal to 0, then we think about the first derivative of our general function. That tells us that 0 is going to be equal to c1 times I, because when we differentiate we get an I coming out of this term, minus c2 times I, because we get a minus I coming out of that term when we differentiate it. And you can plug those, so let's call those 1 and 2, and so equation 1 will tell us, and you solve these however you prefer doing it. Got c1 is equal to 1 minus c2, which I'm going to plug into equation 2, and that's going to give me that 0 is equal to I, 1 minus c2 minus c2. And so putting this all together, I end up with my c2 is equal to 1/2, and then based on this equation over here, c1 is also equal to 1/2. So finally I can get my specific solution is that u of t is equal to 1/2 e to the it plus 1/2 e to the minus it. And I hope that you look at this and go, but this is weird, because we started out with a differential equation that didn't have any complex parts at all. This was entirely a real equation. and yet somehow along the way we seem to have got a complex solution, which doesn't somehow feel right. And in fact, if you ask the question, is this in fact complex? The answer is no. It just looks complex. So it's not really complex. How can we see this? Well, we're going to use Euler's formula. So just to remind you, Euler's formula says that e to the it is equal to cos of t plus I sine of t. So we can use that to simplify our u of t. So we plug into our u of t, and what do we get? We get u of t is equal to, well, that's going to be a half cos of t plus a half I sine of t. And then for this term over here, we're going to get a half cos of t again, because cos of, this will be the cos of minus t, but actually cos of minus t is the same as cos of t, so that doesn't change. But our sine is an antisymmetric function, so we will get a minus I sine t here. So we get a half minus I sine t. And the good thing about all of this is that this complex term cancels with this complex term. So in fact, we just end up with cosine of t as our final specific solution in this case. So there are two things to notice here. The first thing is, yay, we got a real solution to a real differential equation. So actually there was no weirdness. It was just that the apparent complexity came in because we were solving the way we did. But our actual solution is real. This is great. And the second thing to notice is we can see why this is called the undamped case, because here we just have a cosine that just keeps oscillating. So our system just keeps oscillating. There's nothing that will bring it back to being stationary at equilibrium. It just oscillates at the same amplitude around equilibrium all the time. And we can just add in a graph just to remind ourselves of what that looks like. There's our solution, just oscillating ever onwards. So this is your kind of original simple harmonic motion solution, the first thing that you studied in Intro to Physics around waves and vibrations. And then once you start thinking about adding in damping and things like that, then the solutions start to change. So this is the basic one. But now let's think about adding in some damping. So not as much as we had in the very first case that we looked at. So not so much that the system just immediately turns to equilibrium or immediately decays down to equilibrium, but enough damping that gradually the oscillations are going to decrease in size. So that's what we're dealing with here, which is the second case here, the underdamped case. Okay, so we saw the undamped case just oscillates at the same. Now we're going to do an underdamped case. So you can work through this in your own time in excruciating detail. I'm going to move fairly quickly through it. It's just a root finding exercise and then rewriting things using Euler's identity. So here we're thinking about a building. So it has a roof mass of 10,000 kilograms and quite a high spring constant, 40,000 newtons per meter. And now we're going to think about having a damping of 20,000 newtons per meter. So we want to see if our building had these parameters, what would happen if it experienced a slight movement away from equilibrium. Okay, would it oscillate madly? Would it slowly decay down? Would it immediately decay down? Let's have a look and see. So we're going to imagine that our roof gets set in motion with an initial velocity. So at time t equals 0, it's got a velocity of 1/4 meter per second. And initially at time 0, it hasn't moved at all. So its initial displacement is 0. Okay, so imagine suddenly at time 0 it goes boom and gets pushed out. What do we get? Well, remember our characteristic equation here is going to be 10,000 r squared plus 20,000 r plus 40,000 is equal to 0. And you can go straight ahead and find the roots of that. The thing that I would probably do at this point is divide through by 10,000 just to make life easier, because I struggle with all the zeros. And then notice that this becomes a lot easier. Notice we've got a 0 here, so we can divide through by every. We're actually just finding the roots of the equation r squared plus 2r plus 4 is equal to 0. So that's a lot better. And if you find the roots of this, what we get are our first r1 is minus 1 plus I root 3, and r2 is equal to minus 1 minus I root 3. So notice that these are a complex conjugate pair. Oops, conjugate pair. If you're doing something like this and you don't get a complex conjugate pair, you've done something wrong, because your solutions to a quadratic, when both parts are imaginary, will be a complex conjugate pair. So we already saw that in the previous case. Over here, our undamped case, we saw conjugate pair, and we're seeing it again here. Okay, so that's just a little mental check to have. All right, so we can plug those in to get our general solution. That's going to give us a u of t is equal to a constant e to the minus 1 plus I root 3 of t plus c2 e to the minus 1 minus I root 3 of t. Okay, and again, don't panic. We see that there are, our solution looks complex, but hopefully we're going to be able to use Euler's formula to sort this out. So let's just carry on looking. We want to find our specific solution with these initial conditions. So our initial conditions, and you can plug in and find C1 is equal to minus I root 3 over 24, and C2 is I root 3 over 24. And again, notice, so in the previous example, where we were dealing with the undamped case, our constants that we found were real. So the underdamped case is slightly different. Our constants have turned out to be complex, but again, we're seeing that they're a complex conjugate pair. So again, mental check for yourself. You should have a complex conjugate pair here. Okay, so putting this all together, what does our specific solution look like? Well, it looks like u of t is equal to minus I root 3 over 24 e to the blah 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 plus I root 3 over 24 e to the minus 1 plus I root 3 over t. And this might look more worrying than previously, because we've got these i's sitting over here, so it seems like maybe this is definitely complex. But we can use Euler again to help us out. And if you do that, and I encourage you to work through this, what you will find is that actually your final solution does not have anything imaginary in it. You get this rather delightful equation here. So we get root 3 over 12 e to the minus, whoops, no I there, so e to the minus t sine of t root 3. So we do have an oscillatory component here. We've got the sine bit over here, but we also have a decaying exponential that's multiplying that oscillation. So if we grab the picture from the textbook, what this solution looks like is this. So think about what our building did. So there was a sudden gust of wind for our skyscraper and got pushed out of equilibrium. So it started at equilibrium. So remember, equilibrium is 0. It got pushed and moved, and then immediately started heading back, went back to equilibrium, went to the other side a little bit, but not nearly as far because it's being damped, got a little bit further, started to correct, and has eventually, because here is our 0 line, been brought back to equilibrium. So this is a situation where we have enough damping that even though there is a little initial oscillation, it's damped right down and we head back to equilibrium. So let's talk a little bit more about the general case. We've seen the underdamped and the no damping case. There's a little bit more to say. We've looked at 2 examples, and you would basically go ahead and solve like this. But we can actually make things a little clearer, because one of the things you might wonder is, what is the frequency of our oscillations, either in the no damping case over here? So what is the frequency there? Could we work it out based on the differential equation? And similarly, there is a kind of a frequency here that it might be useful to know. So we can do a little bit of algebra to make this more clear. So we have our roots that we know how to find, and it's going to turn out to be convenient to define this first term in each of the roots, c over 2m, as alpha, and this part of the term in each of the roots as omega. So both of those are real valued quantities, because you can see straight from there. So alpha is coming straight from c and m, which are both real, and in fact omega is also only includes m, k, and c, which we've already said are all real. And we know that omega is bigger than 0. And in fact, because we assume that our damping is bigger than 0, it follows that alpha is bigger than 0. And you can do a little check, but omega and alpha both have dimensions of inverse time, so per second, if you want to think about it like that. But they play quite different roles. So using this very helpful notation that we have here, our first root is going to be minus alpha plus I omega, and our second root is going to be minus alpha minus I omega. So again, it's a complex conjugate pair. And so if we use alpha and omega in our general solution will look like this. It's going to have our constants, so it always has our C1 and our C2, which we'll solve for in the specific case, and it has e to the, and here are our roots. But now we can do a little bit of extra work and make things a lot clearer. So we can use Euler's formula and a bit of algebra to rewrite e to the minus alpha plus I omega t, which was this part, in terms of alpha e to the minus alpha t, and causes and sines. And you can do the same thing with the other term in our final solution, and bringing it all together, what you end up with is an equation over here, which looks a little bit hairy, but is actually not bad at all. So our term here, what have we got? We've got, there's our decay term, e to the minus alpha t, and here's an oscillating term, and we've got some constant multiplying that, and then over here we've got a whole similar term in sine rather than cos that's imaginary. And now finally, if we do a final little thing, we're going to define this constant over here, c1 plus c2 as d1, and d2 as this bit over here, then we end up with this solution over here, which now is a lot more intuitive physically to understand. So we've got, it's a real valued general solution in the underdamped case. And you can see straight off that we've got our damping happening in each of these terms and our oscillatory bits happening in those terms. So this is the most general underdamped solution. You can work either way as far as you like. So you could solve the problem the way we did here. There's nothing wrong with doing it like that. And then comparing solutions, you can see that this must be our omega over here and our alpha is up here. Or you can think about it using our alpha and omega right from the beginning and solve like that and end up. So it's entirely up to you. The key thing is being able to go from the initial equation through the complex bit and get to your real solution at the end, because the real solution is kind of what we're looking for, and understanding the real solution is really what's important. Phew, okay, so that was complex, haha. Spend some time getting comfortable with this. Always have your mental checks that anytime you're solving something that has a complex solution, you should end up with a complex conjugate pair in this situation. So things to think about based on our real valued solution. We can actually tell quite a lot. So the presence of, we've already said, the presence of our sine of omega t and cos of omega t means that we have an oscillatory solution and that the radial frequency is omega. So the frequency, the angular frequency, you might have called this. If it turns out that we have a positive damping coefficient, then we find that our minus alpha is equal to minus c of 2m, which is less than 0. So our solution decays because we have a damping term coming in. On the other hand, if our c is equal to 0, so there's no damping, then alpha is equal to 0. And if you think about what that's going to do over here, it's going to make each of these terms over here equal to 1. So we don't have any damping and we just have an oscillatory solution. So in fact, we've now folded in the case with no damping into our underdamped case, but we needed to kind of work through both of them first. So the final thing that we want to have is what's called a definition of the natural frequency, which is our omega in radians per unit time. And when c is equal to 0, so we don't have any damping, then the natural frequency is just root k over m. And that might actually kind of jog a memory from Intro to Physics. Phew, okay. So it would be nice to say that we're done, but we are almost done. Remember when we talked about way back at the beginning, I think back up here, I put a little star here. We need to deal with the case where our roots are equal a little bit later. And that's what we need to deal with next. Because so far, we've always had our R1 and our R2 are different. But if you recall, we said that if you have that our two roots are equal, then we don't have linearly independent solutions. And we needed two linearly independent solutions to make our general solution. So we still need to deal with that, what happens when our roots are equal. But before then, I think it would be a good idea to just work through an example for yourself, and that will look at the previous cases. So I'm not telling you which of the cases it is. See if you can figure this out, and then come back and check. And after that, we will go on to the critically damped case, the case when we have two equal roots. Okay, so give this a go and then come back. Alright, so let's look at our final case, what's called the critically damped case. So this is the case where the coefficients basically conspire so that we don't have two different roots. We have identical roots. Let's have a look at an example. So we look at this innocent looking differential equation, second order linear constant coefficient homogeneous. We know how we do this. We solve this with a characteristic equation. So in this case, our characteristic equation will be r squared plus 4r plus 4 is equal to 0, which factorizes down into r plus 2 all squared is equal to 0. So this gives us two roots, but they're equal. Our roots are r is equal to minus 2. So here we would say this is the root of r is equal to minus 2 with multiplicity 2. And we've already seen that in this case we can't form the most general solution by taking the two roots, because our general solution would end up being something like u of t is equal to c e to the minus 2t. And we want to be able to find general solutions, which if we put in initial conditions, we can always find a c1 and a c2, and we can't really do that over here. This is not a general, because technically what this c is over here is a c1 plus c2. So we need to find some other specific solution that we can use to form our general solution. And what we do is something quite cunning. So we say, well, we will take as our first part of our general solution our u1 of t equal to c1 e to the minus 2t. So that's what our normal first term would be. But for the second term, we say instead of having a constant in front of our exponential, we're going to let that be some function of time. And we're hopefully going to find that function of time so that this term is also a solution. So we're hoping to find some function of time, which when multiplied by an exponential also gives us a solution to our differential equation. How can we possibly sort this out? Well, in order to check that this crazy u2 of t is in fact a solution, we plug it back in the original differential equation and see if we can find what that c of t should be. And if we can find a c of t that works, then we're good. So to find our c of t, we're going to sub back in our original equation. So if we go back up here, our original equation there for our example. So let's just make a note here. This is going back to our example. Here is our, whoops, that should be a plus. So we're going to sub our u2 of t into that equation. Now this is going to get a little bit hairy. Please watch all the terms, but don't get afraid. It gets better. Okay, I'm just giving you a warning. We're going to end up with a lot of terms, but it's going to get better. So if we're going to substitute this crazy u of t into our differential equation, we're going to need the first and second derivatives. So let's take the first derivative. So if I take the derivative of this term, remember now our c of t is a function of t, so when we take the derivative we need to remember this is a product. We need the product rule. So taking the first derivative is going to give me a c dashed of t times e to the minus 2t, and now I need to take the derivative of the e term, so that's going to be a minus 2 c of t e to the minus 2t. And right about now is where you see just terms everywhere, because now I'm taking the derivative of the derivative, and each of the terms in the derivative is a product, so we need to end up with 4 terms, because we're going to get 2 terms from here and 2 terms from here. Let's go straight ahead. So I'm going to get c double dashed of t e to the minus 2t minus 2c dashed of t e to the minus 2t. So that's the derivative of the first term. And now the second term is going to give me a minus 2c dashed of t e to the minus 2t. And then I'm going to get a plus 4ct e to the minus 2t. I think I got those all right. Sure. Okay, so now we can take all of these and substitute them into our differential equation. And basically what we're going to do is we're going to set that equal to 0 and then find the c that makes this true. So here we go. So I've got to plug in for this. So that's going to give me 4c of t e to the minus 2t minus 2c1 of t. In fact, we can combine these two. Yeah, we can combine those two into a minus 4c prime of t e to the minus 2t plus c double prime of t e to the minus 2t. So that's substituted in that. Now I need 4 times this bunny over here. So that's plus 4c of t e to the minus 2t minus 8c of t e to the minus 2t. Okay, so that's this term done. And now finally I just need plus 4 times c of t e to the minus 2t. And we want this all to be equal to 0. This part okay. And this is the great bit, because this all looks a little bit hairy, but you'll notice that we have a 4c t e to the minus 2t, and here's another 4c of t e to the minus 2t, but over here we have minus 8ct e to the minus 2t, so those all cancel. Yay! So we don't have any terms that just involve c of t. And then if you look a little bit further at our first derivatives, we've got a minus 4c prime of t, and we've got a plus 4c prime of t, so those cancel as well. And so finally we're left with an equation which looks like this. C double prime of t e to the minus 2t has to be equal to 0. So that's great. Okay, that's a lot simpler. And in fact, if our u2 is going to be a solution, then we can conclude, because this bit is never ever equal to 0, so we must have c double prime of t equal to 0 if u2 of t is a solution to our original differential equation, which I'm going to label star here. Okay, well, if the second derivative of c is equal to 0, then what can we conclude? Well, we can just integrate this straight up. Integrate it once to get a constant, integrate it twice. It tells us that our c of t must be of the form at plus b. Okay. What more can we say? Well, what can we say about a and b? Could we potentially let a equal 0? No, we can't, because then our c would just be a constant and we'd be back in the same trouble that we were in the first place. Could we, on the other hand, say that b is equal to 0 and maybe a is equal to 1? That would be the simplest possible answer. Let's check. So let's see if c of t equal to t works. So you want to substitute u2 of t equal to t e to the minus 2t into our equation. And if you go ahead and do that, I'm not doing all the derivatives again, and you'll see that it does actually work. So we've actually done something pretty nifty here. So now we've found a function which is a solution to our original ordinary differential equation that is not of the same form as the first solution we found. So a general, or I should perhaps say a general to our differential equation that we had up here is u of t equal to c1 e to the minus 2t, so that's the first term, which behaves exactly like we would expect, plus c2 times this new solution that we found over here, t e to the minus 2t. And that gives us a general solution which we can use to find a specific solution for any initial conditions. Pretty cunning. So we can summarize all of this to the procedure for the critically damped case. So we say critically damped is when we have two equal roots. In that case, your general solution is going to look something like this. So it's going to be a c1 e to the minus alpha t, which is exactly the usual first term, but the second term is going to have this factor of t in. So you can either remember the technique that we just learned, or you can remember, if you get a case where you've got double roots, then you need to basically try and find a solution of this form over here. This is in fact a more general technique, and if you were to carry on studying differential equations, you'd encounter this technique used quite a lot. It's called reduction of order, and it also works more generally. So if ever you're in a situation where you know that you need to have two specific solutions to form a general solution to an ODE, and you've only got one because of repeated roots, you can try this trick again, which basically says try a solution where you let what would have been a constant in your solution be a variable, and then try and find the function to replace that constant. Okay, so we have covered all the possible cases for our second order linear constant coefficient homogeneous differential equations now. I know there was a lot, but hopefully you can draw it all together into a kind of coherent picture if you work through a few examples. One more thing that we need to talk about. You might be wondering, okay, can we always find solutions? It seems like we've covered all the cases. Well, the good news here is, yes, you can always find a unique solution. If you definitely have a second order equation, so this m is equal to 0 is counting out the case where you don't have a second order equation. If you have a second order equation, which again is constant coefficient and it's homogeneous and it's linear, then you can always find a unique solution for any initial conditions. So that's pretty straightforward. In fact, it's even more straightforward than it was for the first order equations, and delightfully, and this is something we haven't even talked about, the solution exists for all t. So kind of these second order equations are kind of the best possible case scenario. So let's just finish by summarizing everything that we talked about this week. So we're looking at this particular kind of second order differential equation, and because we're mostly trying to model physical situations, we're thinking about our mass as being positive, our spring constant being positive, and our damping being positive. And if we do that, then we saw that we have four particular cases. So the first case we have is the overdamped case. So this is when our c squared minus 4mk, which appears in our roots and is always the square root of it, is positive. Then we have real roots, and we end up having just straight decaying exponentials. Then we looked at two cases where we end up having complex roots, and having a look at that, we saw that we get oscillatory solutions If it's an underdamped case, then the oscillations will be decaying, so they'll get smaller and smaller. If it's an undamped case, then the oscillations just carry on. And you can talk about the period of the oscillations or the frequency. So we did a little bit of that as well. So our undamped case has a natural frequency which is related to K and M. And then finally, the last case that we had a look at was the critically damped case, where we had to find an additional solution, and our solution has a slightly unexpected form where we have a T over here. So the one thing we haven't done is draw any of those solutions, and I would encourage you to do that for homework. We will talk a little bit more about this probably in the future, but you'll find if you plot this that our solutions do decay to zero and they don't oscillate. So it's quite similar to the overdamped case, but the form of the solution looks a little bit different. So plot it for yourself. Okay, so that covers everything that we're doing for this week. So please do spend some time working with some of these second order equations, just getting comfortable, finding the roots, deciding which case you're in, and trying to plot some of the solutions that you get, just so that you're comfortable plotting, whether you're using MATLAB or Wolfram Alpha or whatever you like. All right, so give that some practice, and I will see you in the tutorials.